Hello everyone, welcome to this video. In this video, we will be solving this question which states that prove that the dihedral group of order 6, it does not have a subgroup of order 4, right? If you remember what is a dihedral group of order 6, it is a group of symmetries of an equilateral triangle, right? So we had this triangle, if we call this by A, B, C, so you can either rotate it by 120 degree or 240 degree and then by 360 degree, which is 0 degree. And you can take the reflections along these three lines of this particular triangle, correct? So corresponding to this, we have 3 rotations and 3 reflections, each of which are R0, R120, R240, L1, L2, L3, correct? Now for this D3, if you remember, we have already constructed its Scalar table. Now we'll be making use of this table and we'll be seeing that if we are able to find a subgroup of this group D3 having order 4, so such that it contains 4 elements within it. So let's have a look here. So here I say the possible orders of the subgroups, they could either be 1, 2, 3 or 6. Why? Because the order of the group is 6, and by the Lagrange's theorem, for any finite group, the order of subgroup divides the order of the group. So what are the possible subgroups? The subgroup having order 1 is just containing the identity element within it, and that of order 6 is whole of the group D3, right? These are the two non-proper subgroups, trivial subgroups of D3. What about the other subgroups? The subgroups of order 2, they are R0L1, R0L2 and R0L3, which each of which consist of identity element together with a reflection, right? And the third consists of all the 3 rotations. So can we construct any other subgroup apart from these subgroups? Can we have a subgroup of order 4 here? So what we can do, we can try to construct a subgroup, say H, by taking any 3 elements, because if we take, and you can also start by taking any 2 elements, right? So here I took one example where I took 3 elements. Now I'm saying if I wanted to make it a subgroup such that it has order 4, what we have to do, we have to make it a subgroup somehow. So what we have to do, we have to add the remaining elements here, and the remaining elements would be obtained by checking these 2 properties. One is the closure property, another one is the inverse property. So the inverse of each element should be here, and when you compose a new element, the third element should also be present here within this particular subgroup, right? So here, if you compose this R120 with L1, let's have a look at our Scalar table. R120 with L1, you would obtain L3, right? And L3 is not a member of H. So what you can do, you can add this L3 to this H, so that now we have 4 elements. Now let's check whether this is a subgroup or not. I say it is yet not a subgroup. Why? Because when you compose R120 with L3, you get L2, right? And L2 is not present in H. However, it should be present for it to be a subgroup. Hence, what we say in order for H to be a subgroup, we have to add this L2 also within H. So if you add L2 here also, so now we can check whether it forms a subgroup or not. So the answer is no. Why? Because when you take the inverse of this element R120, right, its inverse is R240, and it should be present in the same set H. However, it is not present. So what we can do, in order to make it a subgroup, we can include R240 also within this subgroup H. Hence, we have our subgroup H as R0, R120, R240, L1, L2 and L3. So now does it form a subgroup? Yes, that is a sure shot yes. Because why? Because it is whole of our group D3 and it is a trivial subgroup. So you see, we try to make a subgroup of order 4 here. You can try by taking different elements, and of different order you can start by taking this R0 and R120. So for this, let me show you here only. The inverse of this should be there. What is its inverse? That is 240, R240, as we have just seen. Now what is R120 composed with R240? Let's have a look. R120 composed with R240, it is R0, which is also already present here, right? And the inverse of R0 is R0. The inverse of R120 is what? It has R240, and the inverse of R240 is 120. So that means no other element had to be added. So here it just becomes the what? It just becomes the subgroup of order 3, which I have already listed over here. Hence you see, if you take any other combination apart from these combinations, you will either end up by in any of these subgroups and would not obtain a subgroup of order 4. Hence in this case we have proved that the dihedral group of order 6, it does not have a subgroup of order 4. So I hope you understood this question well. That is it for this video. Thank you for watching.